So, welcome back. Today we are going to look at how NMR data is acquired and how we actually detect the signals. Before going to that, let us recapitulate what we learned yesterday. So, one thing is we were looking at two different pictures. One is called classical mechanics picture, another is a quantum mechanical picture. So, let us start from classical mechanics. So, in this picture which is shown on the screen, so the spins are actually denoted by what is called as this arrow. So, this arrow essentially represents one particular nuclear spin, and as I said in the last class, there are two motions associated with it. One is called the precession, Larmor precession, which is going around the magnetic field, and of course other is the spin, the inherent spin of the each nucleus. So, now there are two possible states when you put a spin in the magnetic field. We call one as alpha state, other as beta state. So, now if you take a collection of spins, so let us say you take a sample which has a large number of spins, each spin can now be denoted by an arrow and it will look something like this. So, here it is like a cone and all the spins are now randomly distributed around the cone, and this is called random phase approximation. So, all the spins which are in the alpha state will be in this plus z direction, and on the beta state we will denote it in the minus z direction. So, as we saw last time, according to the Boltzmann law, there are more spins which are in the upper state, that is in the low ground state, that is alpha state, than spins which are in the beta state. And therefore, if you do the vector addition and subtraction, you will see that finally what you end up is with a small net magnetization pointing in the positive z direction. So, this is what we will call as net magnetization, and all the NMR experiments 1D, 2-dimensional, 3-dimensional, and all the experiments now will deal with this particular spin in the different directions. So, now we will see how we can actually excite these spins and get an NMR signal. So, for exciting, again we saw in the last class, we use the word resonance. So, when you apply an energy which is exactly equal to the energy gap or almost similar to the energy gap, the molecules will now go from ground state to excited state. That means a spin which is sitting in the ground state, in the alpha state, now will flip a spin and then go into the beta state only when an energy is supplied which is of the order or the same range as the gap in the energy levels. So, now how do we apply this energy? This energy is applied in form of a radiation. So, this is now the next part of the NMR experiment, where you apply an energy which is called as RF pulse or RF radiation. We will see what is a pulse in a few slides from now. So, you apply an RF radiation, and this radiation will have a frequency which is given by omega equal to gamma B0, and this frequency is now equal to the frequency or the energy in the of the gap. Now, this frequency, so now let us look, this is from the quantum mechanical picture. Now, let us look at the same situation in a classical point of view. So, what we are looking at is the spins are now precessing around the magnetic field with a frequency omega is gamma B0. So, when we apply a energy radiation which also has the same frequency, this is the same frequency as the rotation of the spins, we use the word resonance, because now they are in the same frequency and this is called resonance. Now, to understand how this particular radiation can cause a transition from ground state to upper state, we have to use a very important concept in NMR which is known as rotating frame. So, rotating frame is what we will see now. So, before that, let us look at how a wave can be visualized. So, this is a simple electromagnetic wave radiation, and you can see we are plotting here in the y axis is the intensity, or we call it as we use the word amplitude versus time. So, this is a standard concept of a wave, and it is given by this equation where y is the y axis, amplitude is equal to the B1, that is the strength of the magnetic the radiation, multiplied by cosine omega t. So, one thing we have to keep in mind here, very important in the NMR perspective, is that every electromagnetic wave, if we discussed in a few last class, it has two components. One is called the electric field and another is called the magnetic field. So, in NMR we do not look at the electric field, we only look at the magnetic field of that radiation, of the electromagnetic radiation, the magnetic field component. So, magnetic field component is what is going to interact with the spins, because spins are also magnets. So, magnets will interact with magnetic field, and therefore, we use the word B, the letter B for magnetic field. So, what we are seeing here is that we have applied a radiation which is now a wave of a frequency omega and it is having an amplitude B1. Now, this wave can also be visualized in a circular manner, in this manner. So, this is what will be very useful when we go to the rotating frame concept. So, you have to now imagine the wave in this particular form. So, this is same as this. So, this is two are called interconvert. I mean, this is basically the same picture shown in a different format. So, here it is showing like the wave is oscillating in a circular manner, and you can see that it is the B1 is now this the amplitude, this particular this vector, and it is now moving around in circle. So, this is called a phase. So, it accumulates a phase with respect to time. So, this concept, this omega into t, is called a phase. So, this is very similar to what is shown here. So, for example, when the theta is 0, it is along this axis, that is y is full 100%. Then and it goes slightly goes to the xy plane. Then when it comes here, the y component becomes 0 because it is now exactly along x axis, and x component is maximum, and then it goes down, it comes to minus y, minus x, and so on. So, this is how the wave is circulating, and this is how we can visualize this RF radiation being applied to the sample. So, on this picture on this side, what is shown is the component. Suppose let us say you are absorbing the component along y axis, then the component is basically somebody is, for example, is sitting here at this point where the arrow is pointing and is looking at the wave. What he will see is that initially the amplitude is maximum, then as the wave is going to the x plane, the y component slowly decreases, it goes to 0, then it goes to the negative y, then again it comes back to 0 and goes to positive y. So, basically it is something like an oscillation here. So, that is what we say that it is applied along y axis. So, let us say that we again now look at the classical picture. So, this is our spin which is rotating in the along the z axis. So, it is around the z axis, this is a magnetic field. So, now this rotation, if it is synchronized with this rotation, in other words, if I apply an RF radiation whose rotation is synchronized in resonance with this particular spin, then we can it causes resonance or it causes excitation. Now, let us look at the concept of rotating frame of reference. So, this is very important here from NMR point of view. So, again look at this picture here. So, this is our vector arrow which is our spin, and this is what I showed you earlier is spinning around the z axis. So, here the spin is not shown, but you can imagine that this vector is moving around. Now, you apply an RF radiation, which again if you refer to the last slide we showed, it is actually oscillating in the particular axis. So, let us say it is going in the y plane, it oscillates like this back and forth. So, now if this oscillation, that is the oscillation which was shown in the circular form, is synchronized with this oscillation which is happening along z, then we can think of it what is called a rotating frame. A rotating frame of reference means you go into a frame in which the speed of the RF radiation or rotation of the RF radiation matches the frequency of RF radiation matches that of the spin. So, you can think of an analogy, for example, in a train. Let us say there is a train which is moving at 100 kilometers per hour and you are standing outside the train. So, for you the train is moving at 100 kilometers per hour, but let us say there is one more train parallel to that original train which is also moving at 100 kilometers per hour. So, if you are sitting in the moving train, the second train, for you the first train will be static because you are now at the same speed, and therefore, the other train does not move at all in your frame of reference. So, this is basically the same idea here, that we go into a reference frame in which the spins are actually moving. So, in that reference frame, for me the spin will not move at all because now it is static. I am also moving along with the spin at the same frequency. So, therefore, this RF radiation which is applied, if it is synchronized with this particular spin rotation, then if I am the RF radiation, you can imagine like that, if I am the RF radiation, for me the spins are no longer moving, they are static. Okay. So, therefore, this is called rotating frame of reference. It is a frame of reference in which the spins no longer rotate because you have synchronized your rotation, the RF radiation rotation with the spin rotation, and that basically the spin appears to be static. So, you have to keep in mind the spin is actually not static, but it appears to be static because we have now entered a different frame of reference. It is like a virtual frame in which the spins are static. So, now this spins, what will happen now is when the spins are static in the rotating frame, what does it imply? It implies that now the spins are 0 frequency because spins are not precessing at all. Why are the spins not precessing? Because they are no longer they are synchronized with the magnetic field, with the rotating field, rotating frame, and therefore the spins are 0. So, when you say the spin omega is 0, what it means? It means that now the external magnetic field itself has disappeared, because remember omega is equal to gamma into B0. So, when omega is 0, it basically indirectly implies that B0 is gone. So, what essentially has happened now, if you think of it carefully, what we have done is by going into a rotating frame of reference, we have actually removed virtually the external magnetic field B0, and only thing which remains now is this particular oscillating B1. So, this is a very important concept which has to be very carefully thought about, and you should I would recommend you to read through the books and understand this concept, because it is a very hard central to NMR is this concept. So, again I repeat is that what is happening is in the rotating frame of reference, we have essentially removed the external magnetic field. Remember, it has not removed physically, it is still there, but in this frame of reference we have removed it, because that the omega is now 0. So, we can qualitatively think of that the B0 is gone to 0, and now only thing what remains is B1. This is also a magnetic field, because remember I mentioned in the last slide that the radiation which is applied is actually the magnetic field component of the electromagnetic radiation. So, now the spins only look at B1, because they have no longer, the B0 no longer appears to be there. So, when they start seeing the B1 and they start moving around the B1, okay. So, they start now moving around the B1, because the B0 is gone and B1 is the what is only remains. So, they start moving around B1. So, remember again, the spins cannot differentiate between B0 and B1. For them everything is a magnetic field, whatever is a magnetic field they start moving around that magnetic field. So, in the first case when there was no B1, it was B0, but by going into a rotating frame we have removed the effect of B0 and we are now seeing only the B1. So, the spins in the rotating frame, remember it is again in the rotating frame, in the laboratory frame, that is when you are outside this frame, in the laboratory frame the spins are seeing both B0 and B1. But when you go to the rotating frame, you are essentially the spins are only looking at B1, and they now start moving around this B1. So, this is like a merry-go-round. So, they actually precess around the B1, which is basically remember the B1 is along y axis. If B1 is along y axis, then the spins will go from Z to go back to minus Z and along in the ZX plane. So, they are actually going from Z to X to minus Z and so on. So, it is like a merry-go-round. The spins are now moving along the B1. Now, so this is what happens into the bulk magnetization. So, this is what I showed you earlier was essentially the rotation of the individual spins. Okay. So, now when you sum up all the spins together, this is what we saw, that you end up with a small net vector which is pointing in the Z direction. So, now our RF field, now B1 radiation is applied along the y axis. So, when the B1 is applied along the y axis in the rotating frame, the Z component, the Z magnetization now will tilt towards x axis. So, this is what we will see now. So, if you look at this bulk magnetization which is along Z axis, I apply an RF radiation along y axis, okay, with some frequency, and now in the rotating frame the external magnetic field is gone. So, it now has to only left with B1. So, this red color vector will start moving around the B1 like a merry-go-round, and it will go from Z to X to minus Z to minus X and so on. So, this is what is shown in this small animation here. So, you see that the vector has come to this, it will go down, it will go this, and it will go back. So, this is what is called the B1. So, what typically is done is that this B1 magnetic field is applied for a very short duration. Then this typical duration is microsecond, and because of this very short duration in NMR we use the word pulse. RF pulse is what is applied. So, this is basically what it means. RF pulse is essentially a very short burst of energy which is given to the spins. Okay. So, the spins now for the very short duration start moving around the B1 field. So, this is why we say it is an RF pulse. An RF pulse is a short burst of RF irradiation applied for a very short time, that is typically microseconds, and then it is switched off. So, a short RF pulse can now, so this is a more important point. The point is we will come back to this in the later slides. The idea here is that a pulse is so strong that it can excite all the spins in the molecule irrespective of their chemical shift. So, when we come to this concept of chemical shift in NMR, we will look at it more carefully, this concept of uniform excitation. But right now the point to keep in mind is that what is done is to excite the molecules from a ground state to excited energy state, we have to do what is called resonance. So, the resonance is essentially a B1 field which is applied with the same frequency as the frequency of the spin. So, it gets synchronized, and in the rotating frame the molecules start spinning, the spins start moving around the B1 field, and that is applied for a short duration of microsecond. Okay. So, this RF field we will look at this again this point later, that this usually is applied at the center of the spectrum. So, what we will do is this particular concept of frequencies and chemical shift, we will come back to it at a later point. So, let us move and see what does this RF pulse cause. So, this is again the same picture which was showed in the previous slide. So, what is happening here is that you have applied a B1 field, okay, and to the magnetization which is along z axis. So, this is called the equilibrium situation. This is basically the situation under which the system has not been disturbed, it is under equilibrium. But the moment we apply this B1 field perpendicular, so this is a very important point here, you have to keep in mind that this is perpendicular to the z magnetization, and when we apply the field, it starts moving around this B1 field, and after some time it would have come to about 90 degrees. So, this is basically a motion which is happening continuously. So, it is not that it is happening in a very discrete manner, it is continuously going round and round like around the B1, again analogous to what I said about merry-go-round. So, this is like a merry-go-round, is going round and round. So, if you start from the first vertical position, it has basically come to by 90 degrees to the x direction. Now, if I go further, a few more duration of this pulse, that is B1, it goes to minus z axis. So, this particular position is called 90 degrees, and if I stop the pulse now at this stage, the spins would be now remaining along this, they will not go further because the B1 will be gone. So, essentially we apply B1 field for a very short duration such that the magnetization, that is the red color magnetization, goes from z and comes by 90 degrees to x. So, this is called a 90 degree pulse. After the magnetization has come to by 90 degrees, we remove this B1, and what happens after that we will see a little bit later, but this is typically the concept of a 90 degree pulse, which you will very routinely often see in all NMR experiment, and this is very important. The 1D is a standard 1D NMR experiment is in fact nothing but 90 degree pulse. So, one should understand what is a 90 degree pulse. The 90 degree pulse is basically duration, the B1 field is applied for a very short duration such that in that time the magnetization comes from positive z axis to the x direction. It can be this direction, all depends on where we apply the magnetic field, but the point here is that it has come by 90 degrees. So, this is called a 90 degree RF pulse, and again remember it is called pulse because it is applied for a very short duration. Now, in some experiments I may want to go further, I may not want to stop at 90 degrees. So, what I will do is again I will start from the beginning, I will take this vector which is along z axis, I apply a B1 field, but this time the duration is not as pi by 2, that is 90 degrees, it is double the time. So, if I double the time of this duration of the pulse, then the magnetization will go further down and it would come by exactly 180 degrees. So, this is called a 180 degree pulse. So, in NMR 99% or 90% of the experiments essentially deal with either a 90 degree pulse or a 180 degree pulse. Very rarely you will see a different angle flip angle. So, this is called a flip angle. So, typically when we use in the jargon of NMR or in the nomenclature, we use the word the flip angle. So, flip angle is basically the time, flip angle is the angle by which the magnetic vector rotates around the B1. So, if it rotates by 90 degree when the B1 is applied, we say it is a 90 degree flip angle. If it rotates by 180 degrees, we call it as a 180 degree flip angle. So, these two types of pulses, the 90 degree pulse and 180, are basically the most important pulses, and this will be the one which will be used always in all the experiments. Now, let us look at what happens when I remove the pulse. So, this is what is shown here. So, this is basically again the magnetization has come by 90 degrees. Now, what I am going to do is I am going to remove this pulse, that means the B1 is gone. So, if you see in this picture it has gone. So, what should happen? So, what will happen is now the moment B1 is gone, we are out of this B1 rotating frame, in the sense we are out of the B1 field. So, the magnetic field goes back towards its original position, that is along B0. So, this is called relaxation. So, relaxation is basically a phenomenon in which the magnetization vector returns to its original position, that is original situation where it is pointing along the z axis, and this happens only when you remove the B1, because as long as the B1 is present, the magnetization keeps on rotating in the xy plane, in the zx plane. Only when you remove the B1, it has no effect of, it has to go back to the original effect, original situation, and that is basically called relaxation. So, this is a very important concept NMR. In NMR there are two things which matters the most. One is called chemical shift, which we will see later, and second is relaxation, which is what is shown here. So, relaxation is basically the return of the magnetization to z axis. So, now when you see what has happened is when the magnetization comes here, when you apply the B1, initially all the magnetization vectors, if you recollect the slides we showed, all the magnetization vector were distributed in a cone, but when you apply an RF field, they actually bunch together, and this is called a coherence. So, what we have done is by applying a B1 field, we have created a coherence. A coherence is basically all of them having the same phase. But when you release the B1, when you remove the B1, they have to go back to the original random phase. Remember the term random phase approximation which was introduced, and that says that when original situation, when it goes back to the z axis, all the spins should be fanned out randomly along the z axis, or they should be distributed along the z axis. So, that process of going from a coherent state, this is a coherent state, to a decoherent state, we use the word T2 relaxation. So, T2 relaxation is the word terms used, you will see often in NMR, and will be very useful when we analyze the 1D NMR spectrum. This T2 relaxation is the relaxation by which the molecule, the spins, go back to the original condition where they are spanned in the xy plane in a random orientation. And the second point is there is another relaxation. So, if you look at this vector again, what is happening here is this vector is now the magnetization is along the xy plane, in the xy plane, but that is not the equilibrium situation. The magnetization needs to go back to z axis. So, this process by which the magnetization goes from x to z is called T1 relaxation. Okay. So, there are two different types of relaxation which are happening at the same time, but there are two different things. So, for example, the first thing, as I said, one is called decoherence, which is the T2 relaxation, in which the magnetization, which is all coherent, they start dephasing. So, remember the word dephasing, they start decoherence. We will look at it again, it will come in many other aspects. It starts decoherence, they got dephasing, and that is called T2 relaxation. And the process in which this vector shrinks, it starts shrinking in this direction and it starts building up in this direction. That process is called T1 relaxation. So, if you visualize in your mind what is this combined effect of these two, you can think of it like a spiral, that the spins are actually spiraling, they are going in a spiral form and they are slowly spiraling and then coming back to the z axis. So, this is what I can draw a picture here. So, what is happening is the spins are essentially they are like this is a vector. So, there are two things, the magnetization has to come this direction and it has to build up in this direction. This is called T1 relaxation. And the other phenomenon is T2, in which all the vectors are pointing in this direction and then they have to start dephasing. That means, they have to start dephasing, and this is called T2 relaxation. So, if you combine these two together, this T1 and T2 relaxation, what essentially you can visualize that the spins are actually going in a spiral form. So, this is what is happening, this rotation, this is x axis, this is z axis, and I can draw a y axis here. So, what is happening in the xy plane, they are rotating and slowly coming back to z axis. This is a combination of T1 and T2. So, this is what happens when we look at T1 and T2 relaxation. So, let us now look at what happens during the relaxation process. So, during the relaxation process, what is happening is the spins have to now this is what is shown here, the spins now start dephasing. This is what I had drawn before, and this is what is happening in the relaxation process. And during this process, when they are actually fanning out, they are fanning out in the xy plane, they are, each one of them is basically as individual spin. Now, if you imagine, these are different spins which are all rotating together, and there is a very famous principle of induction which says that any magnetic any magnet which is rotating induces a current in the coil. So, this is the Faraday's law of induction. So, the magnets, these are all tiny magnets. So, when they are actually rotating in the xy plane, they induce. So, if you keep a coil, let us say we keep a coil here along x axis. When you keep a coil along x axis, these rotating magnets, basically they are all magnets which are rotating now, this induce a EMF in this voltage in the coil, which will be along, let us say, x axis. So, that is what is shown here, that there is a induced current, there is a induced EMF in the coil which is kept along the x axis, and this current you see here is oscillating. And why is this oscillating? The oscillation is coming because the spins are actually oscillating in the xy plane. So, initially they are all bunched together, here red color, so they are all bunched together. So, you get a maximum signal because they are all pointing in the same direction. But as this spins start moving around, dephasing, then they start the vector along x axis, which is all here shown here, starts losing its amplitude because the spins are now dephasing in the xy plane. So, this loss of amplitude is now depicted here in the form of a oscillation. So, this vector, all of them go to the negative axis, they will go negative, then they will come back to positive, and slowly when everything is, all of them have dephased completely, the EMF which is induced is completely gone to 0. So, this is basically the idea of what is called as a free induction decay. So, very important concept in NMR, we use the word FID. So, free induction decay is nothing but the induction of a current in a coil as the spins start relaxing back after the RF pulse is removed. So, this is the signal which is actually captured or detected by a coil which is sitting, let us say, along x or y direction, any direction is okay, and that particular coil captures this signal, and that signal is decaying slowly to 0, and that is because of the rotation of the spins along the xy plane, and this is going to be our signal, and this is what is going to give us a NMR spectrum, which we will see in the next class. Thank you.